come back into frame. Sprocket. Don't work with animals, they said. Hello, Internet. My name is Quinn, and this is Blondihacks. Friends, rail fans, countrymen, this is it. This is the final tender video on the Pennsylvania A3 switcher. In this video, we will finish it completely. We're going to pressure test the feed water system. We're going to put it all back together. We're going to make the tank watertight. And, well, then we're just going to stand back and admire the last 650,000 hours of work before we get into the real job of building a locomotive. Let's go. Here's where we left this water pump. We know that it moves water, but it also needs to be able to force water into the boiler under pressure. The theoretical maximum is 100 psi, which is the blow-off pressure of the boiler. That's the highest it'll ever be under normal operation. However, this pump is actually spec'd for 200 psi because that's the hydrostatic test pressure of the boiler, because Kozo expects you to use this pump for that. I will not be doing that because if you're following this series, you know that my boiler has already passed multiple pressure tests, and I have various other pumps that I use for those tests. So my only interest is ensuring that this pump and all the associated plumbing can stand up to, say, 125 or 150 psi, just to make sure that it will have the oomph to force water into the boiler if the boiler happens to be at maximum pressure. Which is, to be fair, not normally the case. If the boiler needs water, then it's probably going to be low on pressure, so this pump is probably only ever going to see 50 or 60 psi in normal use, if that, but I'm going to test it to the maximum anyway. When we did the first test on this pump, you may recall I had put a temporary spring in here that I'd gotten out of my drawer. It was the wrong size and also not stainless and immediately rusted. I was shocked how fast it rusted. So I did go ahead and make the proper springs from stainless steel wire, as specified in the drawings. I had to order that very tiny diameter stainless wire, but I went ahead and made those springs so I can install those in the valve body. This is the process I used for making those springs. You've seen this before. The same technique I used for making the suspension springs for the tender, just with a different mandrel and different wire diameter, different number of wraps and so on, but the same process. In fact, I did a whole video just on making springs like these on your lathe if you are interested. To the untrained eye, this might appear to be brass square bar, but in fact it is, combined with this pressure gauge, a boiler simulator. This little block is going to hold pressure and allow me to test the pressure pushing capacity of this pump and associated plumbing. To make this square bar into a boiler simulator, I'm going to first chuck it up in the forejaw, get it nice and concentric, and I'm going to turn a fitting on the end that will be for the pipework on the boiler feed water system to connect to. After facing off that end nice and square, I'll turn down most of the end of this stock to the same diameter as the threads on the plumbing fitting that's on the end of the boiler water feed system. I want to test all of the plumbing that's in and around the tender all at once, kind of all in situ, so that the whole system is being checked for weak links when subjected to high pressure. So I'm going to turn this down quite a ways. I'm making the Kozo version of the female side of a pipe union. This is the style of fitting that he specifies in all of his drawings and is the type designed to connect to his plumbing fittings that are on the tender. So it's basically just a normal straight thread on the outside, then a hole down the middle for the water passage, then a small counterbore to take the end of the union cone, and then I part all of that off because I made this an outie and it should have been an innie. How do you even make a mistake like that? Somewhere in that process I realized I'm not supposed to be making something that connects to the plumbing on the tender. I'm supposed to be making something that connects to a check valve. Just like a boiler simulator requires a check valve on all inputs to the pressure vessel, because you can't rely on the check valves in the pump to hold back that pressure. The pressure will bleed back down through the check valves on every pump stroke. So you need a check valve between the boiler simulator and the plumbing stuff that I'm testing. So I did that, and then I put it in the mill, and now I'm drilling and tapping for the pressure gauge that's going to sit on top. Presto, one boiler simulator. It might just look like a complicated L fitting to you, but oh no, it's a boiler simulator. Let's get the tender set up now. I've got an adapter that I had to make to connect the plumbing fittings on the tender to the check valve that I'm going to be using. I didn't show you this because it's yet another plumbing fitting, and we've now already had one video plus 5 minutes of making plumbing fittings. The check valve that I'm using is actually a Stewart Models unit. This was donated by a viewer a while back. The Stewart Model stuff is actually kind of difficult to get over here. It's got a tapered pipe thread on this end, which I had the tap for, so I made that into my adapter. But I'm also putting Loctite 545 on it because I don't trust tapered pipe threads. I've almost never seen them seal properly the first time. Maybe I'm making them wrong, I don't know. And then on the other end, however, this is also a tapered pipe thread, but in a very small size that I did not have a tap for. So on this side, I created a straight thread of the same pitch and kind of jammed it in there with a bunch of Loctite. Not elegant, but it will work well enough for this. If this was going to get used for more than 5 minutes, obviously I would have ordered the tap and done that properly. But now I can get a little tray under the pickup on the pump and get some water in there. And well, let's start pumping and see what happens. I've got the pressure gauge off so I can fill the system with water, get the air out of it, which actually happened very, very quickly. I was surprised how quickly, in fact, as you can see by my being caught off guard and spewing water all over the bench. Then I can get the pressure gauge back on there, again gooped up with Loctite, even though it is a tapered pipe thread, because I hate tapered pipe threads. All right, let's start building pressure and see what happens. Almost immediately, all of the fittings on my simulated boiler are leaking, so, you know, that's a hot mess. I took some time and fixed all of those, and, well, improved them anyway. A word of explanation on this: throughout these tests, you'll see that the pressure drops fairly quickly on the pressure gauge when I stop pumping, and that's because the simulated boiler, that block of brass with the check valve on it, is leaking profusely out of everywhere because the connections are all terrible. But that doesn't actually matter. All that we care about is that the pump is able to build pressure past 100 psi. It doesn't matter if the test fixture can hold that pressure. That's not what we're testing. As long as the pump can build that pressure, then we know the pump is going to be able to force water into the boiler at 100 psi. So don't worry about the fact that it bleeds down really quickly. That said, I don't want the test fixture aggressively spraying me with water, so I did improve it a little bit, just enough so that we can do this test in a reasonably civilized fashion. So we are building pressure now. You can see the pump's having no trouble pushing up to 50 psi. And somewhere around 60 or 70 psi, the first hose clamp gave out on that tender line. That's not part of the test fixture, that does matter. However, that hose clamp had room for more tightening on it, so I snugged that up and that seems to have resolved it. Building more pressure now. At around 100 psi, something exciting happened. The second hose clamp gave up in dramatic fashion. That clamp, however, did not have any travel distance left on it. That clamp was, I guess, slightly larger than the other one. So in order to try and improve that, I put some shim stock in there to increase the clamping force of that clamp. In the midst of doing that, you can see that I pulled back that metal braiding material, that's the heat protection for the hose, because it was just in the way. It was making it really difficult to get the clamp on and off, and it's not needed right at the clamping ends anyway. But when I went to test this fix, watch this crazy thing that happened. Look what's happening to that hose as I build pressure. Whoa, it's a balloon. Crazy, crazy. Then I thought, you know, I don't think I actually checked what the pressure capacity of this hose is. Maybe we should go look that up. I chose it on McMaster because it was the right dimensions inside and out, and it was a nice soft rubber, so it was nice and flexible, and it was also silicone, so it won't mind the heat of a steam engine. I thought, yeah, this is, I'm sure, a good choice. Hoses these days are all pretty high pressure. It's probably fine, right? Oh, look at that. 20 psi is the maximum. So, kudos to whatever design engineer spec'd that hose, because I had 100 psi going through it and it didn't burst. So that was pretty awesome, but clearly this hose is inadequate for the job. Crucially though, that problem did not become apparent until I pulled that metal braiding back from the end. And then it was only ballooning out right in the area where the metal braiding wasn't. So, it seems I accidentally reinvented metal braiding reinforced hose. I did try ordering a couple of alternatives to look at. The first is this stuff here. This is a PTFE tubing wrapped in 304 stainless braiding. So it's built-in thermal protection and it can handle 1500 PSI, impressive, but it's not very flexible. I think it's too stiff for my application. I also found this stuff, which is a rubber hose internally, so it's much more flexible, and it's coated with a nylon or polyester braiding of some sort. And this stuff's rated to 250 PSI. However, it would need thermal protection, so that mesh would have to go back on over top of this, which might stiffen it up too much. Unclear. In the end, I decided to just stick with this stuff that I'm using, and I'll try it on the real locomotive, see how it goes. It's not too difficult to replace these hoses later. I pulled off that old metal braiding that I had cut, put a new piece on back to full length, so it's got that strength all the way down. Then instead of the metal shim, I put a couple of wraps of this stuff. This is silicone tape. It's really neat stuff. It's not adhesive, it just sticks to itself because it's silicone, and that's what silicone does. A couple of wraps on that gave it the thickness that was needed to where that clamp could clamp tightly now. And that did the trick. I can now pump all the way up to 125 PSI, and that clamp is showing no signs of leaking. That seems to have worked very well. The other water line on the tender for the main axle pump has these same two fittings on it that might also be potential leaks that I can't test right now. However, now I know that the clamps themselves do work, and if they leak, then I'll just need to add a little bit of that silicone tape on top of them once again. So fundamentally, the design of these clamps is okay. They just might need a little tweaking in implementation. All right, what is the next weak spot then? With that hose clamp fitting fixed, I go back up to 100 PSI, and a little bit past that, around 125 PSI, the plug at the top of the valve body gives out. So I tried tightening that down, pumping it up again, but that did not fix it. It still leaks around 125 PSI. So that's Kozo's design for a taper seal. It's a 45-degree taper up against a sharp metal edge, and it's not quite enough to seal at 125 PSI, at least not the way I made it. There might be some manufacturing flaws in there. The good news is all the other fittings are bone dry, so those all seem to be working great as designed. All right, take two, testing once again the top of the valve body. That's the current weak point. Looking good, 100 PSI. A little higher, see if we can get to 150. Getting hard to pump now with this high pressure. And 150. Very good. So what did I do to fix that? Yeah, you know the answer. Loctite 545. The magic maker. And in fact, the whole system is now holding about 100 PSI, which is kind of cool, even though, again, holding pressure, not important to this test. Well, I can bleed down the pressure now nice and slowly because that is a successful test. The whole system now is handling 150 PSI, no problem. That's probably 3 times what any of this plumbing is ever going to need to do, so I'm very happy with that. It's a big moment now, though. I can finally install the water tank on the floor pan, and that means sealing it up, hopefully for good. This is a big moment that I've been pretty nervous about, but I've done everything I can think of to do inside this tank. I can't think of any reason why I'm ever going to need to go in here again, so I think it's time. Now, in order to make this tank watertight, if you've been watching this series, you know that the bottom of it is not very flat. I kind of borked it up on the belt sander a little bit, trying to get some twist out of it. I ended up cupping the bottom surface a little bit. So it's too curved for a gasket. It's not flat enough for a gasket, so it needs to have some sort of silicone or other more aggressive sealant on it. My patrons had lots of good suggestions for this, including butyl tape and RTV and combinations of grease and RTV and various marine products and so on. I think there's lots of good things out there that would probably work. What I settled on is good old black bathroom silicone. This is a product that I've used a lot, and I know exactly how it behaves, and I know that it's capable of fixing this joint, so that's what I went with. Go with what you know. If I ever have to take this apart again, it's going to be a little bit messy. Silicone's not a lot of fun when you have to remove it, but I don't intend to ever need to remove this thing, so fingers crossed. I taped up the tank to try and do a decent job of this, try to keep the mess down, and lined it up very carefully, and now we can get some screws in. You could put studs in a couple of those holes to help you line it up on the first try, but I've had the floor of this tender on and off so many times I could do it in my sleep, and I don't need the assist. I had no trouble getting it perfectly aligned and dropping it into place on the first try. It's worth noting that my order of assembly is different than Kozo's. He would like you to do everything that you're seeing me do through the maintenance hatch in the top of the tank. So he has you put the tank on early, and then all of the pump connections and everything are made from above. That does make sense because you have to put the tank together before putting it on the frame, because the frame covers all of these tank screws that you see me installing, and those hard lines that you see install under the frame, so there's a dependency there. However, I tried to install that pump on a dry run through the opening in the top, and I couldn't do it. Like, my hands just could not get into that little maintenance hatch, and it just looked like it was going to be incredibly difficult. What I found, though, instead is that it is possible to thread the frame on over those hard lines. You can kind of sneak it in underneath them, and that allows you to do all of the pump installation, the plumbing and everything, test everything, and then put the tank on. I found that much, much easier. This information is useless to you unless you actually intend to build this locomotive, but just FYI, don't always have to do things the way books tell you to. I mean, usually you should, because people who write books usually know what they're doing, but not always. A little wet finger to clean up the smooshed out caulking. I got some smoosh out all the way around the joint, which is a good sign. That means the joint should be, in principle, all sealed up by that silicone. Silicone is really amazing stuff. It's capable of sealing up pretty big gaps, so I'm confident it can fix my terrible engineering on this tender tank. Then it's time to peel off the tape before the silicone cures. And finally, I did some inspection and a few touch-ups here and there with a wet finger and wet paper towel. I then had to let this all cure for a full 24 hours before testing it. Silicones vary in this regard, but most of them require a full 24 hours before contact with water is permitted. Okay, moment of truth. Let's put some water in this thing and see what happens. Very, very nervous about this. But so far so good. No gushers, that's a good sign. Looking for leaks everywhere. Things are looking pretty good. I'm putting in a little bit of water at a time and then adding a little bit, so I'm testing new joints as the water level reaches those joints, and also increased pressure head from the larger volume of water will expose leaks where there might not have been any before. But so far, it's looking really good. The first leak I noticed was some dribbling around the bulkhead fitting for the drain, so I'll probably take that off and reinstall it with a little bit of silicone. That's an easy fix. And two of the screws for the pump mounting were also dribbling. Again, a little bit of silicone gooped on those will fix that, no problem there. The main seam, though, all looks dry, which is really encouraging. Oh, I spoke too soon. You're on the front corner after a while. There was a little puddle developing right here. Interestingly, this is not the seam at the bottom leaking. This is a leak in the sheet metal slightly above that joint. I knew my sheet metal joints weren't great, so you may recall I gooped up all of those seams on the inside with RTV. However, these shoulder areas at the front of the tank, it was really difficult to get in there with the RTV. I just couldn't get my hands in there. So I'm not too shocked that I missed a tiny spot right there. At this point, the process becomes very much like fixing leaks in the boiler. It's an iterative process involving a lot of light and magnification to try and see exactly where the water is coming from, because I want to make sure I fix the right spot. Once I have a batch of leaks identified, as I currently do, then I got to drain the water out, of course. You can't apply silicone to a wet surface. It's not going to cure properly. So drain all the water out, get everything dry, then go around and patch up all of the leaks that I think I've found. Unlike the boiler, where fixing leaks involves a process from a more civilized age, silver solder, this is a process of gooping up the area with silicone until it stops leaking. It's also a much slower process than fixing the boiler, because after each leak fix attempt, you have to then wait 24 hours again for that new area to fully cure before you test it again. It actually took me 2 tries to fix that front left corner. Interestingly, that's the same front left corner that took 2 tries to fix on the boiler. Coincidence? I ask you. Well, of course it is. Coincidences happen all the time. That's why we have a word for it. What else would it be? As success levels grew, I had to reinstall that handrail because those screw holes are, of course, leaks. I sealed those up with Loctite. Now, as you can see, the tender is completely full and 0 leaks. That deserves a standard Whitworth double fist pump of victory. During these tests, I got lots of practice filling and draining the boiler, and eventually figured out that the urethra pipe is a really convenient place to slide on a rubber hose, which makes draining much easier. Perhaps this was the design intent of that pipe, but hey, this is going to happen to us all as we age. Now to put my money where my mouth is on this reassembly procedure. As I said, from the dry run, I was pretty sure it's possible to slide the frame in under the pipes, thread this needle as it were. The drain pipe was a little tricky. That was actually not there during my dry run, so dodged a bullet, but it is in fact possible to get over and under and through all of this hardware and get the frame installed. I do actually think this is a better way to install it than what Kozo intends. 2 of the frame mounting bolts go through the floor pan, so I also Loctited those, just in case, so they don't dribble. For the hose clamps, I put little pieces of that silicone tape underneath them to, again, take up that space, as I mentioned earlier, and provide some probably unnecessary anti-chafing. Now the trucks can go back on. I had to clean these up with some Scotch-Brite. They were sitting on the bench and they got flooded in one of my many waterborne disasters during this testing, and they flash rusted because they are made of 1215 steel, which does rust quite easily. So I put some anti-corrosion spray on them as well. Now flipping this thing over is not so easy. It's getting very heavy. And all the handrails and hatches and so on can all be reinstalled. And there it is. 1/1/16 scale Pennsylvania A3 switcher locomotive tender, fictionally liveried in Canadian Pacific. It's done. It is completely done. Well, it's almost completely done. There is still a light to go on the back. That's a duplicate of the headlamp on the front of the locomotive, so when we make that, we'll be making 2 of them at that time. But more importantly, it's time for another CAT scan. Let's get the QC inspector in here, see what she thinks. Workmanship in the coal bunker, a little suspect, but otherwise, the final rating is vague disinterest. That is an 8 out of 10 on the CAT scale of emotional response. Very, very happy with that result. Obviously, there's lots of little errors, little things that I could have done better, and I certainly will do better next time, but overall, I'm just frankly amazed I got to this point. Now, we're just missing something in this area here. What would look good there, I wonder? Thank you very much for watching. Thanks to my patrons for making all of this content possible, and I will see you next time. We're in it now, kids.